Swayam Prabha. Digital India. Educated India.
So, the theorem that we will be proving is that uniform NC1 is in L and NL is in uniform AC1. Okay. And when I say uniform, what I mean here is log space uniform. Okay. So, yeah. So, how does the proof go? So, to show that uniform NC1 is in L, what I have to show is that given a circuit, okay, so basically if I am given a circuit, well, I am not just given a circuit, but I am what I am given is a log space machine, okay, which given n can actually produce that circuit. Okay. So, given such a machine, so therefore, I can assume that I have this circuit. What I will show is that given any input to that circuit, there is some other log space machine which can actually decide whether that input belongs to that language or not. Huh? Yeah. I mean, what about a specific input? So, it is generating the circuit, but now given an input, that input, I mean there are 2 to the power n inputs of that same length. Now, how do you know that which input lies in the language and which does not? Okay. So, what we will show is that any NC1 circuit can be simulated in L. Okay. So, what is the idea? How would you go about doing this? So, let us look at a pictorial proof first, and actually it is quite easy. So, we have this circuit C and we know that it has depth some order log n. How can I simulate this in L? Okay. So, essentially what we do is we do a DFS of this circuit. We start at the output gate, okay, and then we do a DFS. So, what I am doing in the DFS, so at every step of the DFS, whenever I come to a node, first I will explore its left subtree. I will try to compute whatever is the output of the left subtree, okay. Then I will take that, I will store that one bit, whether it is the output is 0 or the output is 1. Then I go to the right subtree, I compute the value of the right subtree. Now I have already stored the value computed by the left subtree, so I will use these two values, and depending on whether that gate is a AND gate or a OR gate, I will compute its output value, okay. So, because otherwise, so if let us say I do not call this as uniform, okay. So, I will come to that, okay. So, that is a good question, I will come to that. Let me just complete this discussion and we will come to that, okay. So, let us look at the algorithm. The algorithm is, as I said, quite simple. So, do a DFS of C starting at the output gate, and what do I do in the DFS? At every gate, what you do is recursively or you do not have to even have a recursive algorithm, you can design an iterative algorithm for this. At every gate, compute the value outputted by the left subtree, okay, and store it, then similarly compute the value of the right subtree, now using these two values compute the value at the current gate. Okay. So, essentially observe what are the things that we are storing. At any gate, essentially what we have stored is the path that I have taken to reach that gate. What is a path? A path is just a sequence of left and right. Okay. So, from the parent, which edge am I choosing to go to the next child? Okay. Or we can think of it as follows, that from a node, whether I came from a right parent or a left parent or whatever, I mean you can assume without loss of generality that there are two output gates, but essentially at every step I will be keeping track of at any gate, let us say G over here, I will keep track of the path to reach that gate. Okay. This is a sequence of left and right, and let us say if I am going right at some position, which means that I have already explored the left, which means that in addition to that R bit that I am storing, I will also be storing one value, whether it is a 0 or 1 that I had pre-computed earlier. Okay. So, essentially some 2 bits I need to store along this path, and the total depth of this path is log n. So, I will be storing some log n bits. Okay. And once I have done this, when I have completed DFS, I would have gotten the value at the output gate. Okay. So, this is simple. Now, the question is why uniform NC1? So, why we need uniform NC1, that is actually quite clear if you just think for a bit. So, essentially what do I mean? So, when I say uniform NC1 is in L, what do I need to show? I have to show that every language which belongs to this set, for every language which belongs to this set, there is a log space algorithm for that language. Okay. So, let us take a language, because I have L over here, let me take a language M. Okay. So, suppose M belongs to, okay, let us say not uniform NC1, but let us say suppose N belongs to NC1. Which means there exists a circuit family for M, right. Now, given an input, okay, so let us say I am given an input X and I want, so basically now for M I have to design a log space machine, which means that given any X, this log space machine should output whether to accept or reject on X, right. Now, given an X, of course I know the length of X, but what is that circuit? What is the circuit C of N for that X? Or for that input length? I do not know that circuit, and NC1 does not say anything about how that circuit can be obtained, it just says existence of that circuit, right. So, unless I am given some uniformity condition, there is no way of getting it. Now, suppose if I am given that, okay, so suppose M is in NC1, then there is guarantee on how C of n the nth circuit Cn can be obtained. Okay. On the other hand, suppose that M was in L uniform NC1. So, L uniform is just a shorthand notation for log space uniform NC1. Then what I can do is that given any x, I compute what is the length of x. Now, let us say that length be n. Now, I know that there is a log space machine which when given n can produce Cn for me. Now, I get Cn. Now, I run this simulator for Cn which gives me a log space algorithm, and using that log space algorithm I just say yes or no for that x. Okay. So, that is why this uniformity is very important over here. Without this uniformity you cannot prove this. Exactly. Okay. That is the next thing that I was going to say, that you can actually show that if you are given yeah, so even NC1 can have undecidable languages. So, how do you prove that? How do you prove NC1 will have undecidable languages?
One example is to encode the halting problem or any undecidable problem in binary.
Precisely. Okay. So, take any undecidable problem. Okay. Now, you encode it in unary, okay, which means that for any input length, okay, so that encodes, let us say any n basically encodes an instance of the halting problem. So, now for every n, either that n belongs to the language or it does not belong to the language. Now, in unary there is a unique string of every length, right. So, either that string belongs to that language or does not belong to that language. Okay. Now, given a string, there is very easy to say that, I mean it is very easy to design a circuit Cn which will accept that string. Okay. You just take a, well, whatever and or of all the proper literals. Okay. Because now Cn that we want has to accept only one string. Okay. How we get Cn we do not care. Okay. So, there always exists a Cn which would output a which would accept a unary language. Okay. So, I will, yeah, I will not get into this, I will just mention this as a note that NC1 contains undecidable, in fact not just NC1, I mean okay fine, and any non-uniform, well not any, you have to look at the entire input. So, for example, NC0 will not work, in NC0 you can't even look at the entire input.
Yeah, but still it can have undecidable languages, like we can.
No, but how do you, if you do not look at the entire input, see you have to encode the entire input, right. So, you have x1 up to xn.
Yes, but we can just randomly. I mean, intuitively, like we can see. Suppose I can say that okay, I am going for the first case, I am going to see only the first bit. For the second, I am going to see the fifth bit, and like this, I can like for any n, I can have random such bits. So basically, like it can be undecidable. Even for NC0.
But what about the bits that you are not looking at?
Yeah, but we don't care about it. Like, I mean, for example, for any length of the input, I see
There is exactly one binary string which is accepted. Now, if you are ignoring some input bits, you are actually increasing that set, binary set. Okay, so what do you do on those? So, for example, if you are, let us say not looking at x2, no, you have to accept or reject, right? You have to do something. If you accept that binary string, I can actually have, let us say some setting where it should have been rejected, and if you reject, I can create a setting where it should have been accepted. So, because let us say let us look at any binary string, right. So, let us look at okay, let us take an example. Okay, so let us say I have the binary string for n equal to 4, this 1011 should be accepted, all other binary strings should be rejected, right. Now, how do you accept this string? By looking at, let us say, only 2 bits.
No, I am saying for example, if I say that for a 4, for the length 4, I will see whether the second bit is 0 or 1. If the second bit is 0, I will accept, and if the second bit is 1, I will reject. So this is my definition for the circuit of.
So, if the second bit is 0, you will accept, then you are going to accept this also, but this should have been rejected.
So, like this is not my definition. I am just saying that this is a, I am constructing a.
So, that is what I am saying. So, you are the circuit that you are constructing is not correct, because it is also accepting extra strings.
So how to its language is different with
Huh?
trying to give the same a construction for the same language. He's trying to construct a different language.
Yes, but you have to do it for the same language here. What you are constructing is actually accepting a different language.
No, I am saying that we can construct undecidable languages like this.
But then you have to prove that that language is also undecidable, the one that you are constructing.
No, but I think that I think that proofs can exist.
So, I am not sure actually. When you say NC 0, it means that you can only look at constantly many bits of the input.
So even if I look at one bit, so for example, I can, like which bit to look at, I can decide that with the.
Yes, you can decide which bit to look at.
Yeah, so but that which bit to look at, if it is, for example, if I say that for length, for n equals to 0, I mean for the nth, if the, the input is of length n, I will look at the nth bit, for example. This means the way that thing is coming, for example, we see Cantor's diagonalization argument that for infinite strings, that like anything can come. Like we can select such a string where we can't just compute the nth bit. Like there is no algorithm to compute the nth bit. So uncomputable numbers basically. So if I select some uncomputable number and I say that we are taking the digits of the bits of those uncomputable numbers, then we can have the existence. We can show basically the existence of such NC0 in classes. Undecidable factors.
Yeah, not. So essentially, what you are saying is that even so computing each and every bit is undecidable. So there exists a sequence where every bit computing every bit is undecidable. So if you can get the value of even one bit, it makes it decidable. That is what you are saying. In some sense, I am not sure. So that needs a proof actually. How you prove it, but maybe yeah.
Like for example, we can take an uncomputable number. So there are computable numbers and uncomputable numbers. Now uncomputable numbers also have an infinite binary representation, and we say that each time we look at the, either the 0th bit or 1th bit, depending on like what is the bit in that uncomputable number. So that kind of a circuit exists, but we can't compute.
Yeah.
That circuit.
Yeah.
Not circuit exists. The family of circuit exists.
Yeah, family exists. So basically, so Ci kind of gives you what that ith bit is of that. So if there exists a circuit, then you can compute it. Yeah, yeah, you are right. Yeah, maybe yeah, you can show that. Yeah, that is true. Yeah, so then even NC, not just NC0, even like getting one bit, so which is even smaller than NC0 in some sense, it's just a projection. So yeah. Anyway, let me just. Yeah, and in all these things, what is crucially used is the non-uniformity of the class. Right? Okay, so now coming to the next thing, that is how to show NL is in uniform NC1, uniform AC1. So how do you argue that? So we have to argue that every problem in NL, for every problem in NL, there is a AC1 circuit. So here we will use the fact that NL has a complete problem, and what we will show is that graph reachability is in uniform AC1. Okay. So to prove this, let me define a predicate. So what is the graph reachability problem? So the graph reachability problem is the following. So it's a tuple given G, S and T. It should accept if there is a path from S to T in G, and if there is no path you reject. So that's the graph reachability problem. So I define a predicate reach U V I. Okay. So this is equal to 1 if there exists a path from U to V of length at most 2 to the power I, okay, and it is equal to 0 otherwise. Okay. Now how can you show? So now we will argue that we can actually, given UVI, I can actually compute this predicate in AC1. How would you do that? So essentially I have to give a log depth circuit, but now I am allowed unbounded fan-in.
Recursively compute reach UWI minus 1 and W, like whether there exists a vertex in the middle.
Exactly. So what is that idea? So what is the theorem? Huh? So Savage's theorem, exactly. So this is basically just another way of looking at Savage's theorem. Okay. So reach UVI is true if and only if there exists a vertex W such that reach U W I minus 1 is true and reach W V I minus 1 is true. Okay. Because essentially what this is saying is that, well, if I have a path from U to V of length at most 2 to the power I, then there is some middle point in this path, right, some point W in this path. And what property does the middle point have? That this length is at most 2 to the power I minus 1 and the other part is also at most 2 to the power I minus 1, right. So, and now it is easy to see how we can compute this circuit. So here is a circuit for reach. So how do you do the circuit? So we can write essentially just encoding this. So reach U Vi is equal to, I take a OR over all W in G reach U W I minus 1 and reach W V I minus 1. Okay. So basically, and finally what do I have to compute? What would the output gate be? What is, huh? Huh? No, it will be an AND gate, but which gate? I mean, what is the predicate at the output gate? Exactly. So, what we need to compute is reach of S t and log n. Why log n? So, n is the number of vertices. So, any graph, I mean the maximum length path in any graph is at most n minus 1, which is 2 to the power, which is less than 2 to the power log n. So, if I can actually compute this predicate, then I have an answer to reachability, and basically to compute this predicate, what I have shown is that it reduces to computing reach of whatever this for lower values of I. Okay. So, in each level we have 2 layers of gate. So, I have a unbounded fan in OR gate, and then I have a AND gate with fan in 2, okay, and the number of such levels is log n, because if I is equal to 0, then I can just look at the adjacency matrix of the graph and I can answer whether there is a edge or not. Okay, if I equal to 0 means 2 to the power 0 is 1, so it is just checking for an edge. Okay. Huh? OR, this OR has this many gates, right. So, this circuit has OR gates with unbounded fan in and AND gates of, in fact, fan in 2. Okay. So, this is actually, so there is a name for this class as well. So, of course, this is in AC1, AC1 allows us unbounded fan in for both AND and OR gates, but there is a subclass of AC1 called SSE1. Okay. So, AC1 actually stands for alternating circuit, SSE1 is semi alternating circuit. Okay. So, SACI is the class of problems for which so, okay, functions that have polycized order log to the power I n depth circuits with bounded and unbounded OR gates. Okay. So, by definition it is a subclass of ACI and a superclass of NCI. Okay. So, this completes the proof of this theorem. So, what do we have here? So, what we have here is that, well, NC1 is in L, which is in NL, which is in AC1, and then of course AC1 and so on. So, all of this actually can be shown to be in P, which is in NP. Okay. So, think about this. Okay. So, in fact, I will just give this as an exercise to show that NC is in P. Okay. So, given any circuit, any polynomial sized circuit which has log depth, polylog depth actually, it can be simulated in P. Okay. So, think about this. Okay. So, this completes the proof of this result. So, one more result I wanted to talk about, we can actually discuss it next time, but let me just state the result. Okay. So, remember those 4 uh, relations that I showed. Okay. So, we showed that well NCI is contained in NCI plus 1, ACI is contained in ACI plus 1, and we showed that NCI is in ACI. Okay. But we can actually do a little better than that. So, what we can show is that let me just look at the okay. Let C be a bounded Fanon circuit of size S and depth D, then C can be simulated by an unbounded Fanon circuit of depth d by k plus 1 and size what is the quantity at most 2 S d into 2 to the power c plus 1 for all c less than d. Okay. Sorry, not c, k. Okay. So, what we are saying is that there is a constant, not there is a constant, for any constant. Okay. So, you take any number, it need not even be constant. Okay. So, think of k as any number that is at most d. Okay. You can choose k to be whatever you like. Then what we are saying is that given a circuit of a bounded Fanon circuit of depth d and size s, I can actually reduce the depth by a factor of k. Okay, so, from d I reduce it to d by k, k can be anything for us, but of course, there is a blow up in the Fanon. So, now the Fanon can be unbounded and there is a blow up in the size as well. Okay, so, the size now becomes s into d into 2 to the power c. So, the size crucially depends, it kind of it is doubly exponential in c, but if I choose c carefully then it might still work for us. So, as an immediate corollary of this, what do we get? We get that NCK is where? So, you can actually do NCK is in unbounded Fanon circuits of polysize and depth order of log n to the power k divided by let me choose a different number here just to keep it so that there is no confusion, divided by log n. Okay. So, essentially what we are showing is that, well, we know that NCI can be done in unbounded Fanon circuits of polysize and depth log to the power in, right. But what I am saying is that I can actually do it even in log to the power in divided by log n. Okay. I can reduce the depth by a factor of log n. And how can I do that? What is the k that I will choose? Exactly. So, I will choose k to be log n. So, if I choose k to be log n, okay, and this is not C, this is K. Okay. So, if I choose K to be log n, then I have 2 to the power 2 to the power K. What is that? That is equal to n. So, 2 to the power K is log n and 2 to the power log n is n. So, then I have n plus 1, S is of course polynomial, depth is of course bounded by a polynomial, so the size is bounded by a polynomial. So, the reason why I need to choose K to be log n is because I need the size to be polynomial, and now if K is log n, then clearly I get this as D, which originally was log n to the power I, and K is log n, which is exactly what I get. Okay. So, the proof is actually quite easy and it is not very difficult, but we will see this next time. Okay, so I will stop here.